It's very exciting to be here. My parents live in Cambridge, so my mother dropped me off here this morning, which was a lot of fun, reminiscent of the good old days. I'm Hannah. I'm a senior researcher at Microsoft and an adjunct associate professor at UMass Amherst. And today I'm going to be talking about two new Poisson Tensor Decomposition models for analyzing large-scale event data sets. Specifically, these models are going to take a whole bunch of country-to-country interaction data, and they're going to learn some kind of underlying latent structure that connects these interactions. And this is joint work with my awesome collaborators who are listed here on this slide. Before I start, though, I do want to give a couple of disclaimers. So first, although I'm presenting our new model in terms of country-to-country interactions, it's actually a super general modeling framework that can be applied to analyze a whole bunch of different count data sets. So don't just think of this as something that works just for these kinds of country-to-country event data sets. Second, there's not much math on these slides. So I prefer to focus on intuition to make sure that people understand the key ideas. So if you really want all the nitty-gritty details, especially for the inference algorithms, they're in our papers. Great. So the starting point for this talk is the idea that international relations are inherently multilateral in nature. Specifically, the behavior of countries or pairs of countries is highly dependent on the network in which they're embedded. So to make this concrete, let's consider a toy example. So here on this slide, the decision of the blue player to attack the gray player might depend on whether green has already attacked red. So if we wanted to study the relationship between blue and gray over the course of this game, or analogously, the relationship between the US and Russia over the course of the 1980s, we wouldn't be able to fully understand it without considering the relationship or context provided by green and red. So in other words, we can't just study country-to-country interactions in isolation. We have to study them as part of their broader network. So for decades, political scientists have studied the relationships between countries by collecting and analyzing pairwise event data that looks like this. So each row on this slide corresponds to a single event, and each event is characterized by 4 pieces of information: a time step t within which that event took place, a source or sender country I, a target or receiver country J, and an action type A. And usually these action types come from some kind of ontology. So here, for example, they're from the Weiss code. So where do these events come from? Well, they're extracted from news articles. So for example, the last event here, 900731 IRQ KUW mobilization, might have come from this headline here. July 31st, 1990, Iraq increases troop levels on Kuwait border. And just to be clear, this means that these events represent media coverage of real-world activity as opposed to something more fundamental. But since most people only experience this kind of activity via the news, this is a pretty standard thing for political scientists to do. So back in the dark ages, researchers extracted events manually, often by training student coders to apply a set of coding rules. Then, having curated a database of such events, they could then sift through the data to find latent structure connecting particular sender countries, receiver countries, action types, and time steps. And this structure could then be used to address the fundamental question of foreign policy: who did what to whom, when? But here's the thing. Human-curated databases like this are very time-consuming to construct. Therefore, they're generally very small and often specific to particular regions or periods of time. Because of this, there have been several recent efforts to automate the event extraction process using modern machine learning and natural language processing tools. And this is great. It means that scholars can study events extracted from millions of news articles from all around the world. But the net result doesn't look like that neat table on the previous slide. Instead, it looks more like this giant hairball mess. So unsurprisingly, these events are very, very noisy. They're often full of errors. And there are far too many of them for a human to sit down and sift through by hand. So to make these data sets useful for political scientists, historians, journalists, media scholars, and others, we need some way of taking millions of noisy pairwise events and automatically uncovering latent structure that reveals who did what to whom when. And today I'm going to focus specifically on one particular type of latent structure, overlapping communities of countries that take certain kinds of actions toward one another. And this might look something like this, here on this slide, or something like this. We can think of the process of uncovering this latent structure as a form of measurement modeling. Because we can't just go and measure community membership or community-to-community interactions in the same way that we can go measure somebody's height or weight or record what they ate for lunch, we're going to need a model for measuring communities from these noisy pairwise events. So I want to start by distinguishing between event tokens and event types. So each row here on this slide corresponds to a single event token of a particular event type. So for example, the last row is an event token of type Iraq, Kuwait, mobilization, July 31st, 1990. Another way to represent a data set like this is therefore to count the number of event tokens of each distinct event type. So here, YIJAT is the number of event tokens of event type IJAT. And by aggregating events in this way, we end up with a 4-mode event count tensor, whose modes are senders, receivers, action types, and time steps. Each element of this tensor is a single YIJAT count. And since I can't draw a 4-dimensional hyperrectangle, I've drawn a 3-mode tensor here, whose modes are senders, receivers, and action types. And this is what we'd get if we were to count the number of event tokens of each IJA event types in a single time step. We can then visualize the full 4-mode event count tensor as a series of these 3-mode tensors, one for each time step. And since this is a workshop on networks, I want to point out that a 4-mode event count tensor like this can also be interpreted as a series of weighted multi-networks, again, one for each time step. The nodes in these multi-networks are the sender and receiver countries. Each pair of nodes is connected by a set of weighted directed edges, one for each action type and interaction direction. And the weights on these edges are then the event counts. So for example, the weight on edge A from node I to node J in the network for time step T is the event count YIJAT. All right, well, so far so good. We have this 4-mode event count tensor, but what do we do with it? Well, we're going to decompose it using a Poisson Tensor Decomposition model, and then show that this process enables us to uncover latent community structure. But rather than leap right into tensor decomposition, I'm going to start with Poisson matrix decomposition because it's simpler and build up from there. All right, so let's imagine that rather than an event count tensor, we just have an event count matrix. And specifically, we're going to forget about action types and time steps and just imagine that we have an n by n sender-receiver matrix, where n is the number of total countries in our data set. So a single element, ij, in this matrix is the number of times country I took any action toward country j, regardless of when that action took place. So this is a toy example here on this slide involving 6 countries. And if you squint, you can see that there are 2 blocks in this matrix. one in the top left and one in the bottom right. And we can think of these blocks as sort of communities of countries who interact with one another. In fact, we can recover this community structure by decomposing our count matrix into two n by q factor matrices, where q is the number of communities that we expect to find. So in this case, 2. One of these matrices, the sender factor matrix, represents how active each country is as a sender in each community, while the other one, the receiver factor matrix, represents how active each country is as a receiver in each community. And together, the sender and receiver factors for a single community, so for example, community 1, as I've depicted here on this slide, provide kind of a characteristic signature for that community, specifically who the top senders and top receivers are. So I said that we can uncover this community structure by decomposing our count matrix into two factor matrices, but how exactly do we do this? Well, we specify a probabilistic generative process involving all three matrices by which our count matrix could theoretically have been generated. Specifically, we assume that each element in our count matrix was drawn from a Poisson distribution whose rate parameter is the corresponding element in the n by n matrix obtained by taking the product of the sender factor matrix and the receiver factor matrix. We can then invert this generative process using a statistical inference algorithm to uncover the factor matrices. So just as a reminder, the Poisson is a discrete distribution over the non-negative integers, so it's much more appropriate for modeling counts than something like a Gaussian. It has a single parameter, its mean, so the generative process on the previous slide basically says, on average, our event count matrix should look like the product of the sender and receiver factor matrices. So what does this generative process look like as math? Well, it's pretty simple. Each yij is drawn from a Poisson distribution whose rate parameter is a sum over the q communities, where the summand is the product of the corresponding sender and receiver factors. And that's it. So what happens then when we move back to the world of tensors? Just as a reminder, our goal here is to take a 4-mode tensor whose modes are senders, receivers, action types, and time steps, and decompose it into latent factors that tell us who did what to whom when. Well, it turns out we don't really need to change very much. All we need to do is introduce two additional factor matrices, one for action types and one for time steps. Then we just assume that each element in our count tensor was drawn from a Poisson distribution whose rate parameter involves the same stuff as before, but now additionally involves the corresponding action type and time step factors. Of course, these two additional factor matrices mean that we're no longer discovering simple communities of senders and receivers, because a single Q value now indexes factors from the action type and time step factor matrices, as well as the sender and receiver factor matrices. We're instead kind of discovering these multilateral relations that characterize who did what to whom when. So I'm not going to talk about inverting the generative process, but you can use either variational inference or Gibbs sampling, and we do have code available on GitHub that uses variational inference, and we're currently in the process of putting Gibbs sampling code online as well. So here's a multilateral relation discovered by our model using the IQ's dataset spanning 1995 to 2012 with monthly time steps. The time step factors are in the top row, while the factors for the top 10 senders, receivers, and action types are in the bottom row from left to right. And if you look at the time steps, you'll see that there are 3 spikes, one around 1999, one around 2001, and one around 2008. And the top 3 senders and receivers are Serbia, Albania, and Kosovo. So what is this? Well, it's the Yugoslav wars. The first spike is the Kosovo War. The second spike is the Macedonian insurgency. And the third spike, around 2008, is Kosovo's declaration of independence. So here's another example. This multilateral relation was discovered by our model using the GDELT dataset spanning 2011 to 2012 with weekly time steps. And there are 2 spikes here, one in June 2012 and one in September 2012. And the top senders and receivers are Ecuador, the UK, the US, Sweden, and Australia. Does anyone know what this is? Yeah. This one is all about Julian Assange. So he's the founder of WikiLeaks. He's an Australian national who was under investigation by the US and Sweden for various crimes. And then in June 2012, when he was facing extradition to Sweden, he sought asylum at the Ecuadorian embassy in the UK, which he was then granted in September 2012. So I hope these examples kind of illustrate that the multilateral relations uncovered by this model do appear to correspond to meaningful narratives about who did what to whom when, involving particular sender countries, receiver countries, action types, and time steps. But here's the thing. While we achieved our goal, namely to take this 4-mode tensor and decompose it into latent factors that tell us who did what to whom when, we also lost our ability to discover community structure in a traditional network sense when we moved from the world of 2-mode matrices to the world of 4-mode tensors. Also, in both worlds, we had to learn separate sender and receiver factor matrices to capture interaction asymmetry. And using traditional network terminology, we also only permit within community interactions and thus can only capture assortative behavior. Here's why. This type of tensor decomposition, which is known as CP decomposition, or CanDecomp, or Parafac, or generalized SVD, and so on, decomposes a tensor by jointly embedding its modes into some Q-dimensional latent space. But suppose we actually wanted to embed each mode into its own latent space. So for example, countries into communities, but action types into topics of actions, and time steps into sort of temporal regimes. And then we wanted to uncover some latent structure that interacts these spaces. Well, it turns out this is exactly what the Tucker decomposition does. So for the next few minutes, I'm going to tell you about another Poisson tensor decomposition model based on the Tucker decomposition. So again, rather than leap right into tensor decomposition, I'm going to start with matrix decomposition and then build up from there. So let's return to our n by n sender-receiver matrix. Another way to uncover its community structure is by decomposing it into an n by c latent factor matrix and a c by c latent core matrix, where n is again the number of countries and c is the number of communities that we expect to find, so in this case 2. And these matrices are both non-negative. So the factor matrix represents community memberships. In other words, how active each country is as a member of each community. This column of factors corresponds to community 1, while this column corresponds to community 2. The core matrix then represents community-to-community interactions. So these elements represent within community interactions, while these elements represent between community interactions. So how do we decompose our event count matrix into a factor matrix and a core matrix? Well, again, we specify a probabilistic generative process involving all 3 matrices, and then we invert this process using variational inference or an MCMC inference algorithm to uncover that factor matrix and that core matrix. This time, however, we assume that each element in our event count matrix was drawn from a Poisson distribution whose rate parameter is the corresponding element in the n by n matrix obtained by taking the Tucker product of the core matrix and 2 copies of the factor matrix, one for senders and one for receivers. Yes.
Can I ask you, it looks very similar to the stochastic block model. Is it
I
something?
will get to that.
Okay.
It's about 4 slides, 5, 6 slides time.
Sorry.
Yeah. Excellent question. I will definitely get to that. Great. So this decomposition is nicer than the previous one in many ways, because it doesn't need separate sender and receiver factor matrices to capture that interaction asymmetry. Instead, it captures interaction asymmetry using that core matrix. And specifically, the core matrix permits both within and between community interactions and can therefore capture behaviors that range from purely assortative all the way to purely disassortative. So what does this generative process look like as math? Well, again, it's pretty simple. Each Yij is drawn from a Poisson distribution whose rate parameter involves a sum over communities for the sender and a sum over communities for the receiver, where the summand is the product of the corresponding community membership factors for the sender and the receiver, and the corresponding interaction weight from the core matrix. And that's it. Okay, so what happens when we move back to tensors? Well, perhaps unsurprisingly, again, we don't need to change very much. The only difference is that we now have 2 additional latent factor matrices, one that embeds action types into topics, and one that embeds time steps into temporal regimes. And then we have this 4-mode core tensor instead of a 2-mode core matrix. So I want to take a moment just to dig into this core tensor. Just as a reminder, its modes are communities, topics, and regimes. But we can equivalently think of this 4-mode core tensor as a set of 3-mode tensors, one per regime. And when we do this, we can then interpret each of these 3-mode tensors as a weighted multi-network, just as we did earlier for our count tensor. However, the nodes in these multi-networks are the communities. Each pair of nodes is again connected by a set of weighted directed edges, but now there's one for each topic and interaction direction. So we can view each multi-network as a set of topic-specific community-to-community interaction networks. Or, in other words, we can think of the core tensor as really being a compression of the event count tensor. So again, I'm not going to talk about inference. We use a couple of auxiliary variable tricks that I don't super want to go into now. But the basic idea is that we use Gibbs sampling, and again, we have code available on GitHub. Before I show you the kind of latent structure uncovered by this model, though, I want to spend a minute or two basically answering that question of how this model relates to some of the other models for count data and networks in the literature. So the punchline is pretty simple. Many other models are actually special cases of Poisson-Tucker decomposition. For example, we can recover Poisson CP decomposition, the previous model, by setting the number of communities, topics, and regimes to Q, introducing separate sender and receiver factor matrices, and constraining the core tensor to be diagonal. We can recover the gamma Poisson infinite relational model by assigning all event tokens of a single event type to the same community topic regime tuple, and then constraining the rows of the factor matrices to be one-hot binary vectors. We can also recover the degree-corrected GPIRM by applying similar constraints, but allowing the rows of the community membership factor matrix to instead be one-hot positive real vectors. The gamma Poisson stochastic block model is also a special case of Poisson-Tucker decomposition, if we consider the matrix setting that I started off with and apply the same constraints that we used to recover the GPIRM. We can also recover the mixed membership gamma Poisson stochastic block model. and the degree-corrected GPMM-SBM. And in fact, even latent Dirichlet allocation can be viewed as a special case of Poisson Tensor decomposition. It seems like a really good opportunity to point out that I actually run a cafe press store where you can buy t-shirts, sweatshirts, and coffee mugs with "your model is a special case of my model" written on it. I do this entirely for the benefit of the community. I make no profit on these products, but I do highly recommend you buy one.
It might save reviewers.
Exactly. Exactly. Yes. Yup. Okay, so I want to dig into the kind of latent structure uncovered by this model. So it is kind of like the stochastic block model or the mixed membership stochastic block model, but we have these additional modes which kind of gives this additional structure. So here are the topics of action types uncovered by our model using the IQ's dataset spanning 1995 to 2000 with monthly time steps. We actually use gamma shrinkage priors to learn the most appropriate number of communities, topics, and regimes for this data set. We found that there were 6 topics with weights significantly greater than 0. Interestingly, the inferred topics correspond really closely to the quad class action categories. So they're verbal cooperation, material cooperation, verbal conflict, and material conflict. So moving from left to right on this slide, the topics place their mass on increasingly negative action types. So topics 1, 2, and 3 place most of their mass on verbal cooperation action types. Topic 4 places most of its mass on verbal conflict action types and the neutral make statement action. And then topics 5 and 6 place their mass on material conflict action types. And I do want to note that the material cooperation action category is absent, but this is not surprising because these action types basically rarely actually occur in practice. So what I want to do now is zoom in on one of these topics. So this topic places most of its mass on consult and intend to cooperate, but no mass on cooperate itself. So it describes the actions of countries that just kind of talk about cooperating. So it's kind of a lip service topic. We can look at the elements of the core tensor that are specific to this topic and, for example, the top temporal regime. And I circled the 2 strongest between community interactions here. So 2 to 5 and 2 to 7. So what's actually going on? Well, the heat map on the left of this slide depicts the community membership factors for those countries whose strongest membership was to community 2, 5, or 7 when taking an action associated with this topic. And I sorted the countries accordingly and then outlined the countries strongly associated with 7 in red, 5 in green, and 2 in purple. And then finally, I've colored each country according to its strongest community membership in the map in the bottom right. And you see that all of these countries are in Europe. And this really emphasizes the geographic nature of the kinds of communities being uncovered here. So community 2 is Western Europe. Community 7 corresponds to the Balkan states, and community 5 is Thrace, the Greece-Turkey region. The core tensor then captures the fact that the Western European countries frequently initiated lip service actions towards community 7 and 5 between 1995 and 2000. And this fits with our historical knowledge. During the Yugoslav wars, which took place in the Balkans, Western European countries famously dragged their feet on intervening. So here's another topic. This topic places most of its mass on make statement, appeal, and disapprove. So it describes the actions of countries that denounce one another. It's sort of a protest topic. And again, we can look at the elements of the core tensor that are specific to this topic and the top temporal regime. And I've circled the strongest between community interactions again, so 2 to 9 and 12 to 9. Again, I've colored the countries. And what I've done is I've colored the countries associated with 2 in purple, 9 in red, and 12 in green. The countries in Community 2 are in Northwest Europe. Community 9 is Russia and Belarus, and Community 12 corresponds to the former Soviet republics. Again, this matches our historical knowledge. Western Europe and the former Soviet states expressed a lot of tension toward Russia between 1995 and 2000. So again, I hope that these examples illustrate that this model really does appear to uncover overlapping communities of countries that take certain kinds of actions towards each other. But even beyond that, and in part because of the relationship to so many of these other models in the literature, I hope I've convinced you that Bayesian Poisson Tensor Decomposition is a super general framework for finding latent structure in large-scale digital archives of count data. So, in the last few minutes, I want to talk about something a little bit different here. And by this point in this talk, I imagine many of you are thinking, wait, but these models assume that time steps are independent. That's a terrible way to model dynamic networks. And you know what? You were right. So for the last couple of minutes, I want to talk very briefly about some new work of ours on addressing this limitation. And this is really very new work. We just presented it last week at the NIPS conference. So to do this, I want to return again to the world of two-mode matrices. But now, I want to imagine that we have a slightly different matrix than the one we were thinking about before. So I want us to imagine that we have an n squared by t event count matrix. So each row in this matrix corresponds to a directed pair of countries, I to j, while each column corresponds to a time step t. So a single element in this matrix, ijt, is therefore the number of times country I took any action toward country j during time step t. And these are actually, the countries aren't real, but the values themselves are actually real values from a real data set. And the thing I want you to take away from this is that this matrix is very sparse. Most of its elements are 0. Moreover, if I plot the count over time for a single country pair, you can see that they kind of hover around 0, but then they're punctuated by these bursts of activity. So it turns out we can uncover communities of country pairs that exhibit sort of similar bursts of activity by decomposing the matrix a couple slides ago into an n squared by q factor matrix and a t by q factor matrix. To do this, we assume that each yijt is drawn from a Poisson distribution whose rate parameter is a sum over communities, q, where the summand is the product of the country pair and time step factors. So this is just a Poisson CP decomposition model, much like the one from the first part of my talk. I'm focusing on a different, slightly different matrix there, but it's very similar to that one in the first part of my talk. So far, so good. But what about modeling temporal dynamics? Well, one way to do this is to assume that each time step factor is drawn from a gamma distribution, whose shape parameter involves the sum over all q time step factors from the previous time step, as well as a q by q transition matrix. And in the interest of time, I'm not going to talk about all the details of this model here, but I want to note that this model, in expectation, matches the linear dynamical system while remaining within the gamma Poisson framework. So we've been able to capture this kind of a dynamical system kind of thing without having to move to using Gaussians. Unfortunately, it doesn't lead to closed-form conditional posteriors, so it's not immediately amenable to Gibbs sampling. But by augmenting the generative process, which I've depicted here on this slide as a graphical model, with a set of auxiliary variables, and then repeatedly applying a set of 3 rules that transform that model, or that graphical model or generative process, we magically end up with a series of alternative generative processes, or graphical models, culminating in this one here. And this series of models allows us to derive a really efficient backward filtering, forward sampling inference algorithm. So I'm not going to go into all the details about this, but I will say it is totally awesome. We had a NIPS oral on this last week, and if you want to learn more, you can either read our NIPS 2016 paper, or I'm happy to have conversations with people about this. So before I stop, I also want to note that there are a handful of other things that we want to do here. What I've done is basically shown you the math behind 3 different models and some, plausible kind of results, things that look reasonable in terms of face validity. The first thing that it's super important to do when developing a model for measuring theoretical constructs in the social sciences is to validate that those latent variables that you're using to measure these theoretical constructs are really valid representations of them. So in other words, what we need to do as our next step is assess construct validity. And there's a bunch of work in the social sciences on doing this. This typically involves assessing 6 different types of construct validity, the first of which is indeed face validity, so those kinds of plots I showed you before, but there's also many other things that we need to go ahead and do. And while I've seen a lot of work assessing construct validity in the context of models for text, so things like topic models, I really have seen much less work on using this process to assess the validity of uncovered community structure. So I imagine that this is going to be a non-trivial process, and it will take us a little bit of time to do. The second thing that we want to do is switch to using data from the Open Event Data Alliance. So we've been using the IQs dataset and the GDELT dataset, and they're fine, but we're very excited to use this much more recent dataset from the Open Event Data Alliance that's sort of continually updated, and they've been very open with their code as well. The third thing we want to do is figure out how to model temporal dynamics, that sort of dynamical system model, back in the tensor framework. So while we've thought about this for matrices, where you have something by time steps, we've not yet, well, we've started thinking about it, but we've not yet finished thinking about how you might do this for the kinds of tensor models that I talked about in the first 2 parts of my talk. So that's really the next big thing that we're going to be focusing on, as well as model validation. And then finally, because we want these models to be used by social scientists, we want to add support for covariates of various sorts. And again, we've done some initial thinking about this, but obviously we still have a lot more to do. With that, I'm going to stop. Thanks.